So in lecture 14, we dealt with some aspects of the calculus as applicable to complex functions. We dealt with the limits, continuity, differentiability, and we looked at the well-known function f of z equals to bar z and analyzed it, and we showed that it was never differentiable. We'll come back to that discussion a little later. However, let's now introduce some more concepts and a new result called the Cauchy-Riemann equation. This will also be useful in determining differentiability of complex functions. Recall that a complex function has the shape f of z equals to u of xy plus I v of xy. So there are two parts of it, real and a complex part, and each part contributes to the entire function. Now, if the derivative df dz exists, then if you write out the Newton quotient formula, the limit of delta x, rather delta u plus I delta v over delta x plus delta y, as delta x goes to 0 and delta y goes to 0, will be equal to some number, some complex number a plus vi, if it exists. Now, when we say if it exists, we mean that the limit approaches the same number along any path. So if you choose 2, 3, or 4 or 5 different paths and compute the limit, then you get the same answer, then you say the limit exists. If you don't get the same answers for 2 of them, then the limit does not exist. So in particular, let us choose 2 favored paths. 1. Let us approach, let us have delta z going to 0 along, let's say, a horizontal path first. Horizontal path. And when we say a horizontal path, we mean there's no change in the height. So in other words, delta y is going to be 0. Therefore, df dz becomes the limit of delta u plus I delta v. Now, sorry, there was an I missing here, over delta x, because delta y is now has become 0. We are only considering delta x approaching 0. So if you expand this, you may want to separate this out, and you can say that this is the limit of delta u over delta x as delta x goes to 0, plus I, limit of delta v over delta x as delta x goes to 0. So this first part there, the limit of delta u over delta x, you recognize that to be the partial derivative, day u dx, plus I. The limit of delta v over delta x is the partial derivative of v with respect to x. Or if you want, you may use the short form ux plus I vx. So that is the derivative along the path where delta y is equal to 0. In other words, along a horizontal path. Now let's repeat the entire thing by considering a different path. This time we shall approach delta z approaching 0 along a vertical path. Yes, there are many other paths that one could choose, but we are choosing these 2 special paths to make a certain connection between these 2 paths. A vertical path, in other words, delta x is equal to 0. There's no change in the horizontal direction, you could say. We're moving in a vertical path. So in this case here, df dz becomes the limit of delta u plus I delta v over I delta y. This time delta y is going to 0. There's no mention here of delta x because that has become 0. So if you expand this, you can say that this is the limit of delta u over I delta y, as delta y goes to 0, plus, now the i's will cancel off in this part here. You'll get the limit of delta v with delta y as delta y goes to 0. Now notice this part here has got a 1 over I. The first one has got a 1 over I. You see the 1 over I here? So what is 1 over I? Indeed, it is minus I. So this becomes minus du dy, minus I, that is, minus I du dy, plus. This, the i's have cancelled off, so this is simply dv dy. Or you may write this as vy minus I uy. This is another way to write the derivative. Now we compare these two. If you look at these two results we've got, we say that they should be exactly the same, irrespective of which path you choose. The blue, these two blue items here should be exactly the same, irrespective of the path. Yes, we know there are infinitely many other paths, but for these two particular paths, at least we should have these two being the same. So this forces a relationship then. So along these paths, we can equate. In other words, ux plus I vx should be exactly the same as vy minus I uy. Now, once we get to this stage here, the game is almost over. We can say we can link up the real parts, and then we can link up the imaginary parts, and then make some deductions. So if we look at the real parts, ux must be the same as vy. And if you look at the imaginary parts, which I shall color now in green, you can say that the vx must equal to minus uy. So this implies then that ux must equal to vy, and vx is equal to minus uy. And these are known as the Cauchy-Riemann equations. These are known as the Cauchy-Riemann equations. So they will be used to test if a function is differentiable or not. An easy way would be to simply check whether these results hold. So I just want to make the important point that these are what we call necessary conditions, not sufficient. Necessary, but not sufficient. In other words, for a function to be differentiable, this must hold. But if this holds, it doesn't necessarily mean the function is differentiable. So for sufficiency, it can be proved, and we're not going to go into the details of this, that all the partial derivatives must be continuous. All partial derivatives must be continuous. So now, if you have continuous partial derivatives, then this is a necessary and sufficient condition for differentiability. Ux equal to Vy and Vx equal to minus Uy, and all partial derivatives are continuous. That means the function is necessarily differentiable, and if it's differentiable, it will satisfy the Cauchy-Riemann equation. Now, let's take a few examples. Let's take an example. Why don't we just take the example of is labeled number 16 in the book. Let's take f of z equals to bar z again. Recall we discussed this in detail from first principles. So bar z is the same as x minus iy. Show it is not differentiable anywhere. Anywhere. So the solution goes like this. F of z equals to x minus iy. This can be interpreted with a u. This is a v. So you could say u is x and v is minus y. So if you do a calculation, ux is equal to 1. Vy is equal to minus 1. Clearly, ux is not equal to vy. So Cauchy-Riemann equation fails, Thus, bar z is not differentiable anyway. Because 1 and minus 1 could never equal each other, so there's no possibility for them to actually become equal. So the differentiability doesn't hold anywhere. Note also, all partials are continuous. They are both constant numbers here. But this doesn't help us because the thing has failed on one point. There's no need to go into another point to see if it works there. That's why we're not even considering the other half of the theorem, uy equals minus vx. It's not necessarily a test because the thing has already failed. If one part fails, the entire thing fails. Let's take another example now. Let's take the famous f of z equals to e to the z. F of z equals to e to the z. Differentiable everywhere. In ordinary calculus, you know e to the x is differentiable everywhere. And the derivative is e to the x again. So does that happen in complex functions as well? Let's investigate that very carefully. So this time f of z equals e to the z, and z is x plus iy. I want to put this in the shape of u plus iv. That's my objective. I need to get this to be looking like that. It's not like that at the moment. If I do this, e to the x times e to the iy, I'm getting closer. So this can now be written as e to the x, and e to the iy is cos y plus I sine y. Then I can have e to the x cos y plus I e to the x sine y. And now I've got it in the shape here, u plus iv. So once I got it in that shape, it's all set up now for me to compute the Cauchy-Riemann parts and see if it works. So let's calculate. So now we know that u is e to the x cos y, v is e to the x sine y. That's u, and that's v, without the I. So let's now compute ux, partial with respect to x. Remember, we keep y to be a constant, so it remains as e to the x cos y. Vy, this time we keep x to be constant, so e to the x remains the same. Derivative of sine y is cos y. So you can see immediately that ux is equal to vy. So part 1 of the Cauchy-Riemann equations work. Now let's check the second part of the Cauchy-Riemann equations. How about uy and vx? Uy, this time we keep the x part to be constant, so it will become derivative of cos y, which is minus sine y, so it's minus e to the x sine y. And then on this side here, we're going to look at vx. So vx will be equal to, now this time we keep the sine y constant, so it'll become e to the x sine y. And you can clearly see now that uy equals to minus vx. So the Cauchy-Riemann equations are satisfied. And all partials are continuous. How do we know that? Because they are products of continuous functions. Products of continuous functions. Like e to the x is continuous. Sine y and sine x, they are continuous. So all partials are continuous, therefore we can say f of z equals to e to the z is differentiable everywhere. Now what is the derivative of f of z? Well, you can write the derivative in two possible ways. You can either work with the ux part. For example, you can write df dz is equal to ux plus I vx. That will be the derivative. And if you go back to the top, what is ux? Here we go. E to the x cos y, whereas vx is e to the x sine y. E to the x cos y plus I e to the x sine y. Okay, let me massage this a bit. E to the x is a common factor. Cos y plus I sine y. And then what do you recognize about cos y plus I sine y? That's the same as e to the iy. And so you get back to e to the x plus iy, and that's precisely e to the z. So that is the derivative of e to the z, as we have for real numbers. You could also use the approach df dz equals to vy plus I, or minus, this one is a minus sign, remember? Vy minus iuy. Go into the top, you'll see that we derive this result, and you'll get exactly the same thing. Carry out all these procedures, and eventually you will get e to the z. Let's do one final example. That's number 18. And this example here is of sine z. You see, the first question that we have to ask is, how do you write it in the shape a plus bi? So let us look at that first. Example 18. Find f dash z if f of z is sine z. Right? Now, firstly, of course, we have to prove it's differentiable before we find its derivative. So let us check the Cauchy-Riemann equations. So let's try to convert it to the shape u plus iv as a first move. Sine x plus iy is sine z. That's sine x cos iy plus cos x sine iy. Now you might remember there are some formulas to handle cos iy and sine iy. In fact, cos iy is the same as cos y. So this is sine x cos y. And of course, cos x remains the same there. Sine iy is the same as I sinh y. So this is I sinh y. So now you see I've got it in the shape of u plus iv. So this can be called the u, and this can be the v. So u is sine x cos y, and the v is cos x sinh y. Now I carry out the entire procedure. I don't think I'll need to do this in detail because you can do it yourself. Work out ux, you get a certain answer, vx, or vy rather, you get a certain answer. You'll see they are the same. Then you work out uy, and then you work out vx, and then you should find that uy equals to minus vx. Therefore, the Cauchy-Riemann equations are satisfied. And all partials continuous. Then you can say, now f dash z, ux plus I vx. Well, I suppose we should try ux would be, keep cos y the same, so it'll be cos x cos y. And here vx will be minus sine x sine y. So this can be written as cos x cos y plus I minus sine x sine y. Okay, so then let's now reverse some of the things we did earlier on. Cos x. What can we say about cos y? It's the same as cos iy minus, what can we say about sin iy? Sin iy is I sin iy. So this can become minus I sin x sin iy. So you got a case of cos A cos B minus sin A sin B. So this is going to be this is going to become this is going to be a 1, because that's I squared. I sin, this is minus times minus times minus becomes a minus effectively, and eventually this becomes cos of x plus iy, and cos of x plus iy is the same as cos of z. So derivative of sin z with respect to z is cos z, as expected, as in the normal real numbers. Fine, we shall pause here and take this up to another level in the next lecture.